Welcome everyone. In the previous video, we have started discussing microwave transistors, and we started with the bipolar junction transistor. In the bipolar junction transistor, we discussed the pi model, and we said that such pi model uh, depends on, or the parameters of such pi model depends on uh, the biasing and the load condition of the transistor. So it is not quite useful to use the pi model for a wide frequency range. And instead of using the pi model, we can directly measure the S parameters of the transistor. And from these S parameters, we can design the microwave circuits by using the S parameter of this transistor. At the beginning, to measure the S parameters of the bipolar junction transistor, the bipolar junction transistor must be biased at a specific point, and then the input and output ports are representing, in this case, port 1 and port 2, and from port 1 and port 2, we can the S parameters in this case. As an example for biasing bipolar junction transistor, we have this simple circuit. Here is the bipolar junction transistor, and as I said, for RF and microwave, the bipolar junction transistor is NPN. The base is connected to a biasing resistance RB and a choke coil. The rule of this choke coil is that it separates the DC from the RF bus. So any RF signal will have open circuit from this RF choke coil. By controlling the voltage VBB and the value of RB, we can control the value of the current I base. On the other hand, the collector is directly connected to a VCC through a choke coil. And usually in RF and microwave circuits, we are trying to avoid increasing any resistances. So we don't use a resistance for the collector here, for example, because the presence of the resistances will introduce some noise in the circuit, and at the same time will increase the noise temperature and the noise figure of the circuit. So for microwave devices or microwave circuits, we are trying to avoid using resistors as much as possible. For the case of the base, we must have a current limiting resistance R base. But for the case of the collector, we don't need to add a resistance here, RC here. The RF bus is connected through a bypass capacitors. So the RF bus coming from the base through a bypass capacitor to the base, and then goes through the collector, and the output of the network is going through a bypass capacitor, another bypass capacitor. For the RF and microwave signal, this bypass capacitor has equivalent circuit of nearly short circuit. The IV characteristic of such bipolar junction transistor is determined as the relation between the collector current ICE, the collector emitter current, versus the voltage collector, the voltage of the collector emitter, or the emitter collector emitter voltage. So the collector emitter current versus the collector emitter voltage for different values of the base current. This corresponds to the characteristic curves of such bipolar junction transistor. So by adjusting the value of VBB for a constant value RB, we can obtain certain value for IB. Then by changing the value of VCC, we are changing VCE, because VCE is VCC minus 0. So by changing VCC, we can draw the value of ICE as a function of VCE for this value of IP. Then by changing the value of VBB, we are obtaining other IB and so on. The biasing point of the transistor depends on the application of the transistor. For low collector currents, we have the best noise figure. So if you are going to design a low noise amplifier, means that we are going to use low collector current. On the other hand, higher collector currents giving the best power gain. So if we are planning to design a power amplifier, we are going to increase the collector current. So depending on the application, we are going to choose what is the biasing point for such transistor. And for this biasing point, here is port 1 and here is port 2. By using a vector network analyzer, we are going to measure the S parameter S11, S21, S22, and S12. As an example, for a real microwave transistor, NEC NE58 219 with a collector emitter voltage 5 volts and collector current 5 milliampere, we have these following S parameters at the frequencies 0.1 gigahertz, 0.5 gigahertz, 1 gigahertz, 2 gigahertz, and 4 gigahertz. It can be noted here that the value of S11, the magnitude of S11, and the magnitude of S22 is not 0. This means that the bipolar junction transistor by itself is not matched. And these S parameters are measured assuming that Z0 is 50 ohm. So the S parameters or the input and output ports of the transistor are not matched. This means that in the design of a microwave amplifier, for example, it is required to introduce an input matching network at port 1 and output matching network at port 2 to match these ports with the transistor. On the other hand, S21 represents the amplification path. The signal is going from port 1, which is the base, to the collector. So the signal at the collector due to the signal at the base is S21. We can note that the magnitude here, S21, is much greater than unity. Much greater than unity, it means that there is amplification. So greater than unity here, it means that it has amplification. And it is interesting to note that this amplification here, as the magnitude is 12.7 at 0.1 gigahertz. When we reach 0.5 gigahertz, it is nearly half the value, 6.3. At 1 gigahertz, it is 1/4 of the beginning value, it is nearly 3.5, and so on. So effectively, the gain of the transistor, which corresponds to S21, is decreasing by increasing the frequency. And this actually what we are expecting from the threshold frequency from the previous video. On the other hand, the signal from 2 to 1, from the collector to the base, S12, it has very small value. Ideally, it should be 0, because the transistor should be unilateral. Unilateral means that there is no signal is going from the collector to the base. But actually, we have very small value, and this small value is increasing with the frequency. This is briefly figure of numbers of the S parameters for a microwave transistor. And it should be noted here, the rate of decay here, starting from 0.1 gigahertz to 4 gigahertz, we have decreased from 12 to nearly unity. So we say that there are relatively large mismatch at the base, which is port 1, and the collector port 2. This means that the S parameters here is not 0. So we have large mismatch. The gain, which is given roughly by the magnitude of S21, drops quickly with increase of the frequency. On the other hand, S12 is relatively small, particularly at low frequency, making the device is approximately unilateral. This is briefly how to characterize the bipolar junction transistor in terms of its S parameters. And as I said here, its S parameter is for different frequencies, and at each frequency we have its corresponding S parameter. Another type of bipolar junction transistor is the heterojunction bipolar junction transistor, or heterojunction bipolar transistor, which is abbreviated as HBT. And effectively, heterojunction bipolar transistor is an extensive point of research in microwave engineering and semiconductor devices. As an example, for 3 textbooks which are specifically oriented towards heterojunction bipolar transistor are silicon germanium heterojunction bipolar transistors, which is published by Arctic House at 2003, and it has been edited, or the editors are John Chrysler, and G. New. Another similar textbook with nearly the same title is Silicon Germanium Heterojunction Bipolar Transistor by Peter Acheron, and this was published by John Wiley at 2003 too. So these two books has been published at the same year. A more recently textbook for heterojunction bipolar junction transistor is Heterojunction Bipolar Transistor for Circuit Design, Microwave Modeling and Parameter Extraction by Wiley, and it was published at 2015. So the one who is interested in more details about heterojunction transistor, he or she may refer to one of these textbooks. Effectively, the basic idea of heterojunction transistor is that we say that the bipolar junction transistor is N semiconductor connected with B semiconductor connected with another N semiconductor. Usually, this construction is made of the same semiconductor. For example, all of them are made of silicon. So NBN, all of these semiconductors are of silicon. This is what we are calling homojunction transistor. The key point of the operation of the bipolar junction transistor is that the current is going from the emitter to the base and is going from the base to the collector. It is not required that the current is going from the base to emitter. So the current is going one way from emitter to base, from base to the collector. To make the current flow in this way, it is required to make the doping of the emitter is much higher than the doping of the base. So usually the emitter is N plus and the base is B, and the collector is N. In this case, the resistance of the base is much, or it is great. It is great value. The resistance of the base is great value because the concentration of the carriers at the base, which is B, which is old, is small. So the resistance of the base is great, and the value of the carriers, or the number of the carriers in the emitter, is very large compared with the base, which increase the capacitance between the junction capacitance between the emitter and the base. And as we mentioned in the previous video, the cutoff frequency of the transistor is inversely proportional to C pi, or the junction capacitance of between the emitter and the base. So to improve the performance of the bipolar junction transistor, it is required to decrease the resistance of the base by increasing the doping. But if I have increased the doping, there will be current going from the base to the emitter, which is not allowed. So we have some contradiction. I want to increase the doping at the base, and at the same time, I don't want to make the current going from the base to the emitter. To solve this problem, they suggest that, okay, instead of using homojunction transistor of the same semiconductor material, we are going to use another type of the semiconductor for the emitter, such that the band gap of the emitter is much greater than the band gap of the base. The band gap of the emitter is much greater than the band gap of the base. In this case, if I have increased the doping of the base, the carrier still cannot jump from the base to the emitter. So I can increase, in this case, the carriers of the base, and at the same time there is no current going from the base to the emitter. So still the current is going from the emitter to the base, and from the base to the collector. So by using two different semiconductors with different band gap, such that the emitter has a greater band gap than the base, we can use high doping at the base and avoid flowing of the current from the base to the emitter. So in this case, we have two different semiconductors between the emitter and the base. That's why we say that there's different junction, hetero junction. It is not the same. So we have a hetero junction between the emitter and the base, and we still have a homojunction between the base and the collector. This is briefly what is meant by heterojunction bipolar transistor. Let us say that in more traditional bipolar junction transistor, also referred as a homojunction bipolar junction transistor, the efficiency of carrier injection from the emitter to the base is primarily determined by the doping ratio between the emitter and the base. The emitter doping concentration must be higher than the base doping concentration to achieve higher current injection efficiency. So the current is going from the emitter to the base, injection from the emitter to the base. However, lower doping level in the base region result in higher resistance to access the base electrode. So in this case, the resistance of the base is high. To solve this problem, it would require to increase the doping at the base. However, higher doping level in the emitter region result in high base emitter capacitance. The difference of the doping between the emitter and the base will introduce high base emitter capacitance. And this high emitter base capacitance will reduce the cutoff frequency. And in other words, will reduce the maximum frequency at which this transistor can be used in. So there are two key issues limiting the operating frequency of the bipolar junction transistor. The doping of the emitter must be high, and at the same time there is no current flow from the base to the emitter. So to solve this problem, in order to obtain high emitter injection efficiency, a good choice is use of a material for the emitter region with a wider band gap than the base. So to introduce or to have higher emitter injection, we are going to use a semiconductor material with higher band gap or larger band gap, wider band gap in the emitter. So in this case, the carriers from the base cannot jump from the base to the emitter. So the flow of the carriers will go only from the emitter to the base. So due to the adaptation of the wide band gap material for the emitter, the injection of the carriers from the base back to emitter will be minimized, because effectively we have a wide band gap at the emitter. So the carriers from the base to jump to the emitter, it should have very high energy to overlap of this wide band. And the emitter injection efficiency in this case can be increased without direct dependence on the relative doping. Why? Because effectively the emitter in this case has a wide band gap. It means that the carriers already have higher energy, so I don't need to make higher doping such that the majority of the carrier is going from the emitter to the base. So we say that, and the emitter injection efficiency can be increased without direct dependence on the relative doping concentration in the emitter and the base. Therefore, heterojunction bipolar transistor remains the advantage of silicon predecessors and extend them to higher operating frequency. So we still making use of the main advantage of the silicon device or the silicon bipolar junction transistor, but extend it to the higher frequency. Here is a schematic diagram for the band gap of heterojunction, and assume that we are going to use NB, such capital N indicates that it is N with wide band, and small b means that a B type with a small band gap. So these are the energy bands of the N capital and B small before connecting to each other. When they are connected to each other, the Fermi level of the two semiconductor pieces will be the same. So the conduction band of the N type will be looks like this, and the conduction band of the B type would look like this, and the energy band of the B type of the N type here, and here the energy band of the B type. It is interesting here because the band gap here is greater than the band gap here. The energy of the conduction band at the junction here, it would be bent like this to match the Fermi level, because the Fermi level, it should be the same as the junction. In this case, it is interesting to know that we have energy well at this point. This energy well has significant importance. If we have any carriers here with high energy moving towards this direction, it will be trapped at this energy well. However, on the other hand, if we have any electrons with high energy in this direction, which can pass this region, it will have energy well here, and it can continue to the energy band in the following part. So this energy well prevents any carriers to go from the B piece to the N piece here. And this is what is the importance of the heterojunction. So this energy well is the main characteristic of such heterojunction, and as we are going to discuss it in the high electromobility transistor in a following video, such energy well in this region, the semiconductor B here is nearly intrinsic, not B. So in this case, we don't have any carriers or any free carriers in this region. This effectively what prevents the current going from the base to the emitter. So the current can go only from the emitter to the base, but cannot go from the base to the emitter. By combining such heterojunction in a complete transistor, here NBN, where capital N here is the N with wide band gap, connected to B with normal band gap, connected to the N with normal N gap. So capital N here is the N with wide band gap. Here the B and N here are the semiconductor with small band gap, which correspond to the base and the collector. Here the current is flowing from the emitter to the base, from the base to the collector, and it cannot flow from the base to the emitter. As an example here, this B and N are based on gallium arsenide, and to increase the band gap here in the emitter, we are going to use aluminum gallium arsenide. So by controlling the ratio of the aluminum in the aluminum gallium arsenide here, we can control the value of the band gap in the emitter. So this is an example for the energy band diagram of an NBN, where capital N is the emitter, which corresponds to the wide band gap semiconductor, and Bn here is the small band gap. Heterojunction bipolar transistor has base emitter junction made from a compound semiconductor material such as gallium arsenide, indium phosphide, or silicon germanium, often in conjunction with layers of other materials like aluminum. Effectively, the aluminum here, specifically in gallium arsenide and indium phosphide, is used to control the band gap of the emitter. This structure offers much improved performance at high frequencies. Why? Because effectively we can increase the doping at the base, and increasing the doping at the base, we can reduce the size of the base. At the same time, we are not required to increase the doping of the emitter. So reducing the doping of the emitter, or reducing the ratio of the doping of the emitter to the base, will reduce the value of the emitter base capacitance. Reducing the value of this capacitance will increase the threshold frequency. Some heterojunction bipolar transistor can operate at frequencies exceeding 100 GHz. Recent developments with heterojunction bipolar transistor using silicon germanium have demonstrated that these devices are quite useful for low-cost circuits operating at frequencies up to 60 GHz or higher. Specifically, silicon germanium has the advantage of that it can be made with the same technology of the silicon bipolar junction transistor. High levels of monolithic integration are easily inexpensive with silicon germanium heterojunction bipolar transistor. So this technology is providing to be very useful for low-cost millimeter wave circuits. As an example, for the S parameters for a typical heterojunction bipolar transistor, we have example for silicon germanium heterojunction bipolar transistor by Infon, which is DFB 640F, with collector emitter voltage 2 volts and collector current 1.2 milliamperes. The corresponding S parameters here at different frequencies from 1 to 6 GHz looks like this. Once again, we say that the input port and the output port are not matched, so we are still needing a matching network for the input and output ports. Here is S21, which corresponds to the amplification. It is interesting to note that the rate of decay of S21 as a function of frequency is much less than the rate of decay of homojunction bipolar junction transistor. Also, S12 is very small value, which means that this device is still unilateral device. So S21 decreases much less rapidly with frequency when compared with bipolar junction transistor. This device is also seen to be approximately unilateral as S12 is relatively small value. This is briefly what is meant by bipolar junction transistor and heterojunction bipolar transistor. In the following video, we are going to discuss the microwave field effect transistor. And as we said, we have different three types of microwave field effect transistor: MOSFET, MOSFET, and HIM. So see you in the following video, starting with field effect transistor.